Okay, so this, what's in most, at least very many textbooks, until the Dake book came in 19, whatever it was, 80. Most of the textbooks talking about gas reservoirs use the so-called pressure squared equation form, the low pressure assumption, which has got the same constant, and it's just, instead of pseudopressure, you can just use pressure squared. This is not quite right. This is... And that mu z can be at any pressure. Okay? Because if you look at the term mu z, mu times z, in this low pressure range, it's constant. Okay? Basically constant. Okay? So, at initial pressure, whatever pressure you want to use, it's fine. So this is kind of the low pressure equation. Now, why it was used so much is that prior to the at least mid 1960s, probably even late 60s, through the 60s, most developed gas reservoirs were low pressure. Why were they low pressure? Low-hanging fruit. Have you ever heard of the expression low-hanging fruit? The gas price was low, was very low. So you didn't get very much for gas. So you're not going to spend a lot of money drilling deep for gas. But if you drill shallow, you find a big gas reservoir, what the hell? You'll produce it if it's big enough. So most of the reservoirs that were developed through the 1960s were low-pressure gas reservoirs. And this assumption was very simple. Plus, we didn't have computers. We didn't have Excel. And the pressure squared was a much easier way to handle the equations. So that's why the low-pressure equation was known to every petroleum engineer until the end of the 60s, the end of the 70s. Okay. Okay. So I'm going to take this kind of equation here. And now we're going to talk about what if you derive this equation using Forsheimer instead. Okay? What changes with this equation here? You could actually say nothing. Okay? The only change you need to make is how you define the skin term. Okay? Now, what we talked about is that we have some kind of damage or stimulation skin. It's a constant. Okay? But if we say that the total skin, which we would normally write total for everything, is equal to that damage or stimulation skin. Normally it would be a damaged skin, plus a skin that gets worse and worse as the rate goes higher and higher. Okay? Because the higher the rate, that's when we get the higher velocities, that's when we get the extra pressure drop. And what we're going to do is that we're going to say that this extra pressure drop we're seeing here, we're going to express it as a velocity dependent skin, or what we call a high velocity flow skin. Okay? A high velocity flow skin. We're just going to treat it that way. And that's going to be a function of the velocity. Okay? It's a function of velocity. And when you do that, we write the term as a constant times the gas rate. Okay? Gas rate reflects the velocity. And if you do all the derivations, this is what you'll end up getting. And D is a constant, directly related to the beta. That's the term. So the beta, D has got beta in it. If you want to look at the calculation of D, then it has the beta, plus a bunch of other stuff in it. Okay? But effectively, it's reflecting, if beta is 0, then D is 0. Okay? So that's the only change you have to make to handle this more general Forchheimer equation that has the rate-dependent non-Darcy effect. And if you look at the total skin and you ran 3 or 4 rates, each rate you would calculate would have the same KH, but it would have a different skin. And those skins would plot something like this. Okay? And you'd get the slope of this is D, and the intercept is our damaged skin. Okay? With 0 rate. I'm plotting versus gas rate. So if you go out and you run these 4 different rates and you measure the flowing bottom mole pressure at each rate, the only thing changing is basically going to be the skin. Everything else should remain unchanged. Temperature, KH, log RERW, average reservoir pressure. We're talking about running, one day one rate, another day another rate, another day another rate. 4 days, 4 rates. Or you might even do 8-hour flow periods, and in a day you're finished. So if you do that, and then you back calculate, in a sense, the skin, you don't do it exactly that way, but if you did that, you'd find that the skin values were changing. Okay? So I'm going to write it like this because it's easy to remember just one equation for all situations, Darcy and non-Darcy. So Darcy is just simply saying that that's the same equation, but for Darcy, D is equal to 0. Just like basically beta is equal to 0. Okay? if you solve this equation directly for rate, if you try to solve this equation directly for rate, you can kind of see that you've got rate downstairs on the right-hand side and you got rate on the left-hand side. Okay, and so this equation is often solved in terms of rate directly. Okay, and I'll write the equation in that form. I don't know if it should do the algebra or not. I guess we could try to do it. I'll let you guys do the algebra. If we just solve this, I don't remember if A and B. I don't know if A is in front of the Q squared or the Q. Let's just see what Vetkovich uses in his. I don't remember what A and B. And that's the paper. I just want to use the same. Yeah. A on Q. Okay. Like that. Okay. 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 Where A is going to be equal to TR log RERW minus 3/4 plus damage skin over 0.703 KH and B is basically the same constant times D. Okay. So for a given pressure drawdown, you can solve for the rate directly. Just solve the quadratic equation. Okay. So now I'm going to talk about two methods of graphically representing this equation. Okay. So the one which is not very common except unless you're using modern software like Prosper or something. The first is the same as the oil, for oil wells, where we plot PWF on the y-axis versus gas rate on the x-axis. Here we've got average reservoir pressure. And this is going to look something like that. It's going to be curved. This might, for example, be for the case of Darcy flow. Okay? If you add a non-zero D, then this is going to look something like that. That would be with some D greater than 0. So this is the traditional inflow performance relation IPR type plot. Inflow performance relation. And let's say the red is our actual well. We've got, some points. Three-point test, and that's what it looks like. Now, in a year from now, the average reservoir pressure will have dropped, well, maybe 2 or 3 years from now, but at some time in the future, the average reservoir pressure, this is maybe 2010 and this is 2015. So now the average reservoir pressure has dropped. What's the curve going to look like then? Well, the curve is going to be very similar, but it starts and looks something like that. And you can verify that by running a new test, 5 years later, where you've got maybe 3 new points, and it looks like that. Yeah.
This curve should be parallel.
Should be
Parallel to each other.
well, yeah, pretty much. They'll have the same shape, same kind of shape. Okay, so the point down here where PWF is 0, we have a special term for that. And the government regulators, particularly in the United States, are very keen on that number being provided. And it's called the absolute open flow potential. So it's saying that you put in this monstrous pipe, there's no pressure drop in the pipe. The pressure at the surface, you're flowing the well to atmospheric pressure, there's no back pressure at the surface. So basically the bottom hole flowing pressure is 0, or close to it. It's like the theoretical maximum that well could ever make at that particular time. So in 2010, this would be the absolute open flow potential, and we write it AOFP for 2010. In 2015, we've got the AOFP 2015, and so forth. And it's going to continue to decrease. And it's decreasing because the average pressure is decreasing. Not because of the permeability, not because of the scale. Everything else is assumed constant. It's just because the average pressure is dropping. So this is the IPR plotting method of this equation. This is basically what you'll see today in programs, most programs that use this, like Prosper. Okay. But things were better in the old days. Pre-1970, the plot was made differently. In pre-1970, for the most part, we could pretty much say that we could use this pressure squared assumption was okay. Right? Okay. So the method that was used probably pre-1980, but certainly pre-1970, is that on the x-axis we plot gas rate, but now we're going to use a log scale. Okay? And on the y-axis we're going to plot reservoir pressure squared minus PWF squared, or if it's a higher pressure reservoir, then we're going to use pseudo pressure drop. Like that. And this is going to be on a log scale, as is the rate. Okay. And when you do that, you're going to get a curve that looks something like that. And I'm going to label that point. This is when the reservoir pressure is equal to the initial reservoir pressure, and the bottom flowing pressure is equal to 0. Okay? That's this point here. So you just substitute in PRI, put PWF 0, and that's the value that you have here. Okay. The well will never produce more than that rate here. And this rate is what we would call the absolute open flow potential times 0 initially. So that's the initial absolute open flow potential. Now, at low enough rates, the slope of this down here is going to be approximately 1. That's Darcy flow. So basically we're seeing Darcy flow down here at low rates. Shouldn't write D. I'll write D for Darcy. But as you go to higher rates, that dq term, okay, or the beta velocity square term will kick in, and you're not getting, okay, if you didn't have the dq term, for that rate here we'd be able to produce, for that pressure there, you'd be able to produce that rate. Okay? If this is no, that's just Darcy equation. So this is the D is 0. So for this amount of drawdown, you've got the initial pressure equal to the PR and the PWF is 0. You'd have an absolute open flow potential, which this is a log scale, might be 3, 4, 5, 6 times higher than the actual. So this is the actual, and that's so I'm going to put maybe I'll change colors here. pink. Let's say that the field came on in 2010, and we ran this multi-rate test with 3 different rates, and we established that curve. Okay, we got the curve from these 3 different rates. In 2012, we ran a new set of 3 rates. Okay. But in 2012, the average pressure may have dropped to here. So this is in 2012, average reservoir pressure. Okay. So the new absolute open flow potential for this well would be this rate here in 2012. Then we move to 2015. We make another set of measurements. Now the average reservoir pressure is down here. We make 3 more rate. And those fall okay. Now what you see is that this figure, the points as they're plotted, always fall on the same line. That's not the case up here. Okay? Because the A and B contains nothing that should change over time. It might change, but so both of these are constants. And they shouldn't change. I mean, the D is a rock property. Now, the damage could, of course, get worse or get better. So that would, that might change. But certainly the KH shouldn't change. So under the assumption that none of these constants are changing, then year after year, if you do a multi-rate test, you should get the points lying on the same curve. Plus the fact that you're getting all of the historical data in one format. You're not making new points each time. You can't really see on this first method, has something really changed, because the shape kind of looks the same, but you don't really know. Okay. This is this form of the graphical presentation is referred to as the reservoir back pressure equation. Plot, back pressure plot, not equation. The reservoir back pressure plot. Pressure, delta pressure squared, or delta pseudo pressure on the y-axis on a log scale, and the rate on the x-axis on a log scale. And then we hit 2016. You guys can't see this very well, right? Ouch. It's pretty nasty. Okay, I'll change it to, is that better? A little bit? Okay. Not much better? Yeah, it's okay. So now in 2016 we come in, this pressure hasn't changed that much. Okay, and now we get the following data. Okay, what does that tell us? Well, it tells us at the rates that we're producing, these 3 rates during the 2016 test, we had expected to get this pressure drop, right? But we got more pressure drop. Okay? Likewise for the other two rates. For this rate here, we expected to get this pressure drop, but we got this one. Now, who's the drillers in here? Okay? Come on, don't be, you know, who wants to be a driller? All right. I'm giving you a hard time. Okay. Is this good or bad? We got more pressure drop. So you just remember what I've told you. Curtis says more pressure drop is not good, right? It's got more pressure drop. The deviation from the trend of 5 years or 6 years, that's what we call a red flag. Something is wrong with the well. There's got this extra pressure drop that all of a sudden starts showing up, and we don't know why. It could be somewhere it's in the constant A and or B. Okay? Now the only thing that really should change in A or B is what? Is the damaged skin. I mean, KH, that's God-given. Mother Nature, you got the KH. You're not getting more. You're not getting less. Okay? Reservoir temperature? Nope. The D is a rock property? Nope. There is only one thing that can be changing here, and it's skin. Okay? So who do you call? The driller sees this. The driller sees that it's a problem. Who does the driller call? Who removes skin? The production engineer. You remember who you went to class with. You call the production engineer. You say, get your butt out to the well and do something because I want my performance back on the trend that I had initially. Or better. So after the test, they make a decision, a rational decision, to go in and do some operation that costs money, but it's going to cost less money than the production we're going to be losing if it stays on this poor performance. Okay? So this is immediately identifying, it's like a, what do you call it? It's a monitoring system. Okay. Nobody does this anymore. Absolutely nobody. Not even ConocoPhillips Petroleum. But I want to tell you a story about Mike Vetkovich when he went to work. And I don't want to tell all the people outside. I'll tell them. I think he went to work about when I was born, so around 56 or the late 50s or something. And I've told you the story. He was the best student at University of Pittsburgh or not? I don't know. I've told the story so many times. He was the number one top of the class at University of Pittsburgh. And it wasn't a boom, but you know, you could get jobs if you had the best, because at Pittsburgh that's where Muscat was. I mean, it was like like today's Stanford. So he had all the best grades. He was from steel, small town, steel mill in Pennsylvania. And he wants to get a job. So he starts interviewing for jobs. He gets the one rejection letter after the next rejection letter after the next rejection letter. And it's not because the name is difficult to pronounce, Vetkovich. That's another story I'll tell you about a guy who had a hard time in life because his name was too hard to pronounce. George Mitchell, he's the one who started the shale gas revolution in the United States. That's another story for later. He did not get a job because of his last name, Vetkovich. And he didn't have any kind of religious or color problems or anything else. But he didn't get a job. The question is why? The reason was because he had a stutter. He stuttered. Do you know what stuttered is? Yeah. That was it. And it was fairly strong stutter. Didn't get a job. Best in his class. All the companies. Except Phillips Petroleum. And apparently he'd been to the interview, and then there's a couple of famous guys from Phillips called, I think, Smith, Colander and Smith. I don't know who was the boss, but they did some publications there. Anyway, the one says, well, we had this interview. This guy had best grades, Pitt and everything, and everything's good, but he stuttered so bad that I just can't recommend him for a job. And the boss says, what the hell do we care if he talks. If he's got top grades from University of Pittsburgh, he's going to be a good engineer. He's from the steel factory. We give him a job. They gave him a job, and that is the Mike Petkovich, who now kind of is one of the true pioneers in what we did. And of course, you can be sure that Mike Petkovich never left Phillips Petroleum Company out of loyalty for that decision. So anyway, Mike Petkovich, when he went to work for Phillips Petroleum, spent the first 4 or 5 years of his career in West Texas, plodding day in and day out on the hundreds, if not thousands, of gas wells that they had. Going out to every new well, they'd go out, they'd make the measurements, they'd run the multi-rate test, they'd plot the point on the curve year after year, and as soon as it fell off the curve, he called the production engineer, they'd come out, do a workover. Phillips Petroleum was operating their wells optimally, and nobody else in the industry essentially was. They were doing things right. It's because they red flagged performance deterioration immediately. And there was a whole group of engineers, that was their whole job. And today the technology is like gone. Nobody does this for whatever reason. So it's unfortunate because there is a single relationship, A and B, that should last forever from the beginning to the end of the life of the well. Of course, unless something goes wrong. So this back pressure curve is a much preferred way to represent this equation of a straight line. It's very easy to plot. Pressure squared. In the old days, you could use pressure squared. You could do that on a slide rule. You make the plot. And they made the pressure measurements at the surface, so they had this extra pressure drop in the tube. And we'll talk about after Easter. But anyway, this is flagging. There's a red flag. It's flagging a problem. And more than likely, it's a problem that the damaged skin has gone up. Okay.
Curtis?
Yeah.
If you fracture the well, would it be...
It'll shift it to down. Exactly. So if you go in and the production engineer does a really good job, cracks it or really cleans it up, then you can move it. The new curve could even drop below this. That's exactly right.
Could that be also used if you use the fractures and kind of an indication that your fracture, like especially let's say in the shale gas, that your fracture now is closing and then you can do a refract?
Well, the problem in using it for shale gas is that there's so many transients, infinite acting behavior. This is all based on there being more or less pseudo-steady state. I mean, you can use it if each test is the same duration, then you can use, but it's not really so applicable to the shale because everything takes so long. Yeah, you don't reach this. I'll tell you another story. Okay? And if I don't run out of time, I'll tell you the story about the guy with the name. That's a great story. But this is another true story. This is a guy who made vice president in Phillips Petroleum Company in the I think it was the late 60s or early 70s. In connection with the Hewitt, this new, Phillips was doing a pretty good job for being a bunch of Okies. They were part of this Hewitt discovery and development I was telling you about. And there was this engineer, I think his name was Fetters. And he was the engineer was going to go out on the well test, and that well test, because there was different formations, and the reservoir was quite large in area, and there was different ownerships into different blocks. So this well was going to kind of determine the relative proportion of the total field production that Phillips was going to get. Okay? It's called prorationing. You prorate the total field production to the different owners according to how much volume is in their section and the ability to produce that volume. So this was a very important test. And this Fetters, he was out on the rig, and he'd gone through the Phillips school, same as Fetkovich. He knew about this, and it was religion. I mean, because they had file after hundreds of wells, and the points always fell on the same curve. So this was a well test going on, and the performance during the test, he was plotting. This was really high permeability. This is the one I told you it depleted down to 50 psi. It was still making money. So he was plotting PR squared minus PWF squared versus rate. You got the first point, you got the second point. Okay? And then he got let's see, he got the first 2 points, and then he got the third point here. Okay? It looks about like this is actually, we put it in the book. So he's got these 3 points. Now what he could say is that, well, you know, I don't know, this is the trend. Here, this point was off. I don't know if it was that far off. I don't think it was quite that far. It was relatively close, but it was just slightly off the trend. Okay, it's a log scale. You know, it's the week. You know, get off the well. You want to save money, rig time. You know, go home with the family and everything. And you could just kind of say, well, okay, we'll just use this. But this Fetters, he was a smart guy, and he believed in this plot. And with these 3 points, what do you think it's suggesting? Now that you've been hearing me preach this, what do you think it's suggesting? You got 2 points, and then you got a third point that is better or worse? Better. Okay? This well is going to be determining how much money Phillips makes out of this license, the Hewitt Field. So he calls into his boss and he says, I'd like to run an even higher rate. Now realize this is the first gas offshore field in the UK North Sea. And the boss says, there's no way. You get your butt back into, you know, onshore, and we're done with the test. Because they'd kind of maxed out where they were supposed to be. Well, Fetters, Maverick, good, bad, I don't know. He has them run one more rate, higher rate. Falls over here. Before he calls in that he reran at the other rates. This is the number they were going to be using for allocation of what they got instead of this number. It's a log scale. I think it was 3 times more rate they were going to be allocated than with the original points. So what had happened is that the well had cleaned up. There was damaged skin here, whatever it was. These 2 it didn't clean up. You got a rate high enough that you started getting cleanup, and then you went to this rate where you really got cleanup, and then basically you traced up and down. The guy became vice president for a while, but he was a rebel. He probably said what he wasn't supposed to say for a while. That's a true story. Okay, it's too late for the... You guys remind me after Easter to read you. I'll read you the obituary of the guy who started the shale gas revolution. His name George Mitchell. United States. It's not good that he died 3 or 4 years ago, but the obituary is fantastic. So we'll do that later.